Thank you very much, Susan. Thank you very much, Jess, for joining us all the way from North Carolina and during your maternity leave. Very kind of you. Thank you all for being here this afternoon. I'm very pleased to introduce to you Jessie Edwards. She's an associate professor in the Department of Epidemiology at the University of North Carolina at Chapel Hill. She's an infectious disease epidemiologist, and she has an interest in sharpening quantitative methods to inform public health decisions using imperfect and disparate data sources. Her work focuses on asking questions to improve the response to HIV and other infectious disease outbreaks in the US, the Dominican Republic, and East Africa. And the reason I invited Jessie is because I came to know of her work when I attended a workshop a few months ago. And, there were epidemiologists and biostatisticians, some clinician scientists present over there. And I just said, I find that in statistics, we just, of course, this is a problem with statistics. We keep reinventing it in different disciplines and calling the same thing by different names. And really, there's just one or two fundamental concepts that seem to keep reappearing over and over again. And somebody in the audience said, have you heard the work of Jessie Edwards? She's written about this and about how missing data is actually somehow at the base of all the many, the long nomenclature of biases that we have, they're somehow all tied to missing data. And if you could understand that, I think somehow it's like you would just have the key to understanding so many different ideas. So Jessie, welcome, and I'll let you present your talk.
Great, thank you so much for having me. I'm excited to be here and excited to hear any feedback you have on this work. There we go. So the title of my talk is An Imputation Approach to Account for Measurement Error in Marginal Structural Models. I don't want you to focus on this title. It could really be called A Blank Approach to Account for Measurement Error in Blank, because the idea behind the work I'm presenting today is that, as Nandini said, we can view measurement error through this missing data framework that allows us to use very general and familiar missing data methods in a wide range of statistical approaches that we encounter, that we need to use for various problems we run into. And so here, the application I'll show you is in marginal structural models. I do a lot of work in causal inference, but it could just as easily apply to pretty much any approach to data analysis you're using. And so I wrote the paper that Nandini referenced a few years ago. It's called All Your Data Are Always Missing. I should have had a picture of it so you could go find it if you needed to. And it's sort of a tongue-in-cheek title. But the idea behind that paper and this talk is to illustrate that bias due to measurement error can be captured using the potential outcomes framework. And therefore, measurement error can be added to the list of biases you can usefully think about as a missing data problem, like confounding and selection bias. And then I show an example of how you can use that framework and that paradigm to employ approaches to account for missing data when you're accounting for measurement error and in the setting of causal inference. And so this isn't a super notation heavy talk, but I do want to introduce one piece of notation, and that's for the potential outcomes. And a potential outcome is this metaphysical object. So we are saying the potential outcome, so if Y is the outcome for someone in your study, their potential outcome is the outcome they would have experienced under some exposure plan. And we denote those exposure plans using this variable, this superscript A equals 1 in this case. So this Y superscript A equals 1, this is the outcome they would have observed had they experienced exposure plan A equals 1. If there were two possible exposure plans, say A equals 1 and A equals 0, you would have two possible potential outcomes. If there were 10 exposure plans you were looking at in your study, you would have 10 potential outcomes. And so we typically, when we're thinking about a causal question, we think about a contrast in those potential outcomes, such as what's the average outcome we would have seen had everyone been exposed, A equals 1, compared to what's the average outcome we would have seen if everyone had been unexposed. A equals 0. Of course, neither of those things actually happen. So these potential outcomes are inherently metaphysical, which makes some people uncomfortable. And it also necessitates this idea that we have to link those potential outcomes to the data. So we use that using this statement here after the comma, where we say we let the potential outcome y superscript little a be equal to your observed outcome if you actually had exposure plan little a. So let me say that in English, that if we observe that you were actually exposed, then we say that your potential outcome had you been exposed is just your observed outcome. Sounds like a tautology, but it will come into play later in this talk. And so in the real world, everyone experiences only one exposure plan. We don't get to see what happens to you under exposure A and exposure B, or under A equals 1 and A equals 0. So we can never observe both potential outcomes for someone. And this is what people call the fundamental problem of causal inference. And we just to illustrate that, this is a standard presentation of the problem for 4 subjects, I equals 1 to 4, 2 unexposed, 2 exposed, and some continuous outcome for each of them that we get to observe. And we say, well, okay, we observed that this person was unexposed and their outcome was 240. And so we say, well, that's their outcome that we would have observed if they hadn't been exposed. So we put that here, but we don't know what would have happened to them had they in fact been exposed to this particular exposure. Similarly, for person 3, we observed that they're actually exposed. So we don't know what would have happened to them if they had been unexposed. And this is a pretty standard presentation of this fundamental problem of causal inference, where some of the potential outcomes are missing. And some foreshadowing, those potential outcomes are usually not missing completely at random. And so those of you familiar with approaches to work with and think about missing data will have some red flags going off, because when your data are not missing completely at random, it means you might have a biased subset of the data that you get to observe. And so I'll use a toy example over the next few slides to illustrate this sort of standard presentation of causal inference as a missing data problem and how a bias due to measurement error can be represented in this framework. To do this, I'll talk through a hypothetical study about among people with HIV, does infection drug use at treatment initiation affect your CD4 cell count 1 year later? And I'm giving you this very toy example that I made up. This is not real data for the sake of this project, on 600 patients with HIV followed from their treatment initiation for 1 year, where exposure A here, this is injection drug use at study entry. Outcome Y, that's their CD4 cell count 1 year after treatment initiation. And then we have some confounder L. I guess I didn't come up with what that might be, but you could think of, it could be any number of things, such as, maybe some indicator of socioeconomic status or something like that. And for these 600 patients, because I made up these data, I know both potential outcomes. And here, these are no longer, these 4 rows are not 4 patients anymore, but 4 different types of patients. And this N tells you how many patients are in each type or in each group. And so for type 1 patients, there were 100 of them. Had they been exposed, their CD4 cell count would have been 120. And had they been unexposed, it would have been 240. Now, these people had L equals 1, so confounder equals 1, and they happened to be exposed. Now, type 2, had they been exposed, their CD4 cell count would have been 250, and had they been unexposed, it would have been 370. And these people happened to be unexposed. And so on for types 3 and 4. Notice that there are twice as many people in groups 3 and 4 as in groups 1 and 2. Just that will be important for later. And so that we can see from this table that the true causal effect is negative 120 cells. So injection drug use at baseline lowered your CD4 cell count by 120 cells 1 year later. It was bad for you, in other words. And it's easy to see from this table because I've helpfully made the difference in the potential outcomes in all 4 groups exactly 120 cells. So the mental math here is pretty straightforward. And so now that's great. We don't actually get to see the hidden potential outcomes. Instead, we do a study and we observe some data, which I've shown over here on the right. And now we observe the counts, we observe the exposure and the confounder, and we observe some observed outcome. And now note that for people with observe, with people who are exposed, A equals 1, we observe the potential outcome had they been exposed. And for people who are unexposed, the outcome we observe is the potential outcome had they been unexposed. So this is all as you would expect. So once we do our study, we get to observe this bit over here on the right. And this is where, when I give this talk in person, especially with my students, we all have a handout. And at this point, I have them fold the paper. And so you can only see what's on the right of this table, the observed data, and the hidden data becomes hidden from view, like so. And then what we do is we say, well, we observe these data, and like any good epidemiologist or data scientist, we know that there's what we observe, and then there's what we assume to be true for the analysis. And so when we want to do causal inference, we actually make all these implicit steps in our head usually. Usually we don't write them down, but where we say, well, given this observed data, what can we infer about these potential outcomes? And I say imputed here, but this isn't necessarily an imputation process we do as part of our analysis. This is something we're mentally imputing. And so, for example, for type 1, these people in this first row, we say, well, we observe that they're exposed and we see they have an average outcome of 120. So we think we're going to say their potential outcome had they been exposed is 120. This is just this first axiom I talked about. We call this consistency in causal inference. For the second type of person, we see that they're unexposed. So we're going to say, okay, their outcome was 370. And so we're going to say that's their potential outcome had they been unexposed. And same on for type 3 and type 4. And now you'll see this is a standard presentation of the problem where we're missing the potential outcomes after this implicit mental imputation. We're missing the potential outcomes for people who are unexposed. We're missing their potential outcome had they been exposed. And for people who are exposed, we're missing their potential outcome had they been unexposed. So what do we do? And this is usually hidden from our view in epidemiology, but this is what's happening behind the scenes. Well, one thing we could do is we could say, well, okay, we're missing potential outcomes for these people under A equals 1 if they weren't actually exposed. So maybe we should just we could say, well, they would have gotten the average of what we did observe. So for example, we got to see this potential outcome, and for people of type 1 and type 4, we might say, well, if we were missing, let's just impute the average. And that here is 207. Remember, this is a weighted average because there are twice as many type 4 people as type 1 people. And the same thing for the other potential outcome. We'll say for the people who are missing that potential outcome, let's impute the average where we got to see it. And you do that, you get 283. And I'll save you the mental math here. Now, if we want to do a contrast in these potential outcomes, we see that the difference in the potential outcome under exposure and no exposure ends up being negative 77 cells. In contrast to the truth, which we know is negative 120. If we flip over that, look on the other side of the paper, we would see that we've sort of incorrectly imputed these potential outcomes. And why is that? Well, here, what we've done is we've made this assumption that the potential outcome is independent of exposure. Whereas in reality, the potential outcome and exposure are correlated through L, right? L here acts as a confounder in that it both affects the potential outcomes and is associated with A, which is why there are 200 people in these bottom 2 rows. So what do we usually do? This is sort of epidemiology 101, is instead of doing this imputation unconditional on L, we would instead do this imputation of these missing potential outcomes conditional on L, such that when we say, okay, well, we're missing this potential outcome here, I've already filled it in on this table, but imagine it's missing. When we, instead of putting an average of these 2 numbers where we did observe the potential outcome, let's only look in the stratum of L that we're in. So here we see that we're in L equals 0. Well, who did we observe had that potential outcome in stratum L equals 0? Well, those are the type 4 people. So instead of imputing the average here, we're just going to impute this 250 from the type 4 people. Similarly, the potential outcome is missing here in this cell. And instead of imputing the average, we're going to say these people had L equals 1. Well, where else did we get to observe data with L equals 1? Well, it was up here in the first row of the table. And when we do this sort of mental imputation conditional on L, we see that we get back the correct negative 120 cells. And this is a presentation of confounding as a missing data problem. You have confounding because the potential outcomes are missing at random conditional on L. Now, if L, our confounder, were unmeasured, our potential outcomes would be missing not at random, which would imply there's no way for us to stratify or adjust and get back the appropriate values of potential outcomes. And so, of course, this framework, as biases due to missing data, specifically missing potential outcomes, can be extended if we have loss to follow-up. So, for example, now I've taken type 4. This is the same table I showed you previously, but in type 4 now, half of them are missing the outcome. So both of these rows are type 4. You can tell because they are exposed and have L equals 0. And now when we go through this mental imputation process and we fill in the observed potential outcomes, we're now missing both potential outcomes for this group at the bottom. And so that, as you might imagine, creates problems in a variety of ways. The first is that if we do this unconditional imputation, now we're imputing this average of 120 and 250 that is just among the people who were not lost to follow-up. And so we impute 185s over here and same over on the right-hand side. And if we do this unconditional imputation, we see that the estimated causal effect is negative 98 cells. You might be saying, well, that's closer to the truth than we had before we had loss to follow-up, but that's just by coincidence in this example. We still get a biased result because we haven't taken into account the confounder, which is also, I'm not sure if anyone has a great word for this, but a factor that is both associated with loss to follow-up and the outcome, which causes this type of selection bias. Now, of course, this is a very simple toy example. So if we take L into account, we can account for both of these biases simultaneously, where now we're imputing correctly this, the potential outcomes within strata of L. So up here, we're imputing the 250 observed from down here. Right here, we're imputing the 120 from the first type of person up here. And for the people missing all outcomes, we impute both of their potential outcomes based on other people we observe with L equals 0. And lo and behold, we get back our true causal effect, which in this case we can know because we made up the data. Okay, so that was all a long prelude, and sort of the way people, others, much more brilliant people than me in epidemiology, have thought about causal inference as a missing data problem, specifically regarding confounding and selection bias. But what about measurement error? That was my wheelhouse, how I came to this problem. And so I started out by thinking of this expanded table where now we have the same 4 groups of people. We're doing away with the loss to follow-up for the moment to simplify the example, where this first group, these are the type 1 people, type 2, type 3, and type 4. But now each group has 2 rows, and that's because we have this mismeasured, potentially mismeasured version of the exposure A prime rather than A. A was the true exposure, now we have A prime. So for type 1 people, if you remember on the last slide, these are people who are truly exposed, but about 20% of them, well, exactly 20%, have a misclassified exposure such that their value of A prime is 0 rather than 1. Similarly, for the type 2 people, now 20% have a misclassified exposure, so they have A prime equals 1 rather than 0. And so on for types 3 and type 4. So what does this mean? Well, we can crank through the math we used on the previous slides to see what the implications of this type of measurement error are. For example, if we do our first step in filling out this table, we say, well, which potential outcomes can we fill in based on the observed value of exposure and the observed outcome? Oh, sorry, I missed a step. Always the most important step is that we have this, we have the value of A in our data, which here I'm calling A prime. The first step is to think about, well, what value of A are we going to use in the analysis? And what most people do is they skip the step, just like I tried to do in this talk, where they set, I'm calling this A star, and that's the value of A we assume to be true in the analysis. And they say, well, that's just going to be equal to what we saw. We're going to assume that exposure is measured without error. And then we're going to do this imputation of the potential outcomes accordingly. So I'll just assume that A prime is correct. So this A star will have the same values, oops, sorry about that, as A prime. And now we'll do this imputation of potential outcomes where we say, well, this person was observed to be exposed. So I'm going to say the value of their outcome we observed is the potential outcome they would have had under exposure. But now this is where the trouble comes in on the second row of the table, where we say, well, these 20 people were observed to be unexposed. Now we don't know what would have happened to them if they had been exposed, but we think if they had been unexposed, their potential outcome would have been 120. Now we know, because I've showed you the other side of the paper and the true hidden potential outcomes, we know that this 120 should be over here, but now we've put it in the wrong place because of this exposure measurement error. And this is really where all of the bias in exposure misclassification hinges. So let's look again for the type 2 people. Now these people are truly unexposed, but we've called 20% of them exposed. For the truly unexposed people, we've put their potential outcome in the right place. We said we observed their outcome was 370. We observed they were unexposed, so their potential outcome under no exposure is 370. But now for these people, we think that they're exposed. So we're taking their 370 outcome and we're putting it in the wrong potential outcome column. We're saying this is the potential outcome had they been exposed. All right, so what is this important? What does it mean? What happens next? So what we've done here is we've let the potential outcome, we set that equal to the observed outcome if A star equals A, where A star is this variable we're assuming is true in the analysis. And what happens if we do that? Well, now let's crank through and say, okay, well, conditional on L, let's go ahead and impute the other potential outcomes. And so if the potential outcome is missing, let's set it to its expected value within that stratum of L. And if we do this, we see that the estimated causal effect is -46, which is quite far from our -120, even though here we have accounted for bias due to other causes. And so what the big picture message I want you to take home from the last, 87 tables that all looked alike is that we have this value A that's our true exposure. And then through the process of doing our study, we go through a measurement process, whatever it is. And that gives us a value of A prime that shows up in our data set, what you're looking at when you're doing your coding. And we apply a mask of assumptions on top of that to get a value of A star that we use in our analysis. And all of this gets swept under the rug. We never think about this. I mean, I'm including myself in this, in that we assume these are all the same thing. I think sometimes we think on the front end a lot about measurement of our exposures. Often on the back end, we just collapse these two and we say, okay, well, we're assuming whatever showed up in our data set was the value of the exposure we should use in our analysis. And so the next few slides and the example I'll show you is thinking about how we can apply these familiar approaches to missing data to overcome this bias due to measurement error by thinking more about this arrow right here. How can we relax these assumptions to allow us to flexibly account for the fact that maybe the value we're using for A star shouldn't be this naive value that whatever got measured? I'm going to take a breath here and pause for clarifying questions because that was quite fast and many tables. I'm happy to answer questions now or come back around at the end of the talk.
Yeah. Any questions? Looks like you can continue.
I guess
I'll
throw in a question. Thank you so much for speaking with us, Jess. It's just that it seems like there's so much scope for there's measurement error, there's missing data, there's so many levels. that in the end, if we don't make certain assumptions, we'll never have any results. It's kind of my concern, because I'm guessing you're going to say that there's an uncertainty around the measurement itself. And I mean, I'm interested to see how you're going to account for it, but we don't know the direction of that measurement error, correct? We don't even know if it exists.
Right. You always have to have, so 2 points I'm going to respond. Measurement error is an annoying problem for those of us, for everybody, but especially people who are trying to account for it, because you need outside information. There's nothing in your data. Like, it's great. It's so relaxing to think about confounding, because unless you're pretty sure you have an unmeasured confounder, there's something you can do about it in your data, right? You're like, we're going to stratify, we're going to adjust, we're going to weight. Measurement error isn't like that unless you have validation data or some really great prior knowledge, or a sensitivity analysis or something that's really, there's not much you can do in most cases. But then second, I love your point about at some point you just have to make some assumptions or you don't have any results. And that, that I find that very motivating, and I completely agree. And I think that there's this line that you have to walk between how do you express your results to convey the confidence you have in them, so that people understand when something is being presented, the certainty that underlies your assumptions going in, versus something that has really, low potential for violation of those assumptions. If there are no further questions at this point, I'll dive in. Oops. So as I said, the focus of this part of the talk isn't as much on the specific methods I used, as much to show that in this example, I had a question that required slightly non-standard methods to address. And here I used a marginal structural model because I had this situation where there were some exposures that were time varying, and we needed to account for confounding that was affected by prior exposure. And so marginal structural models were kind of the tool for the job in this case. And the frustration that I ran into when approaching this problem is that much of the work in measurement error has been in these settings where people are either in the linear model or in some other very specific use case, and then they're hard to adapt to other settings. And so my hope was that by applying this framework I described on the previous slides about thinking about measurement error as this missing data problem, my hope was that I could come up with something that was more general, that could be applied to the methods I actually needed to use in real life, which is usually not the linear model. And so, with few exceptions, at least at the time I was doing this work, and I know that more examples have appeared since then, most implementations of marginal structural models assume that you have exposures, outcomes, and covariates perfectly measured. And so here I look at a situation where we have some exposure measurement error, and we'll build off that potential outcomes framework to address it. Specifically, the example that got me thinking about this was trying to estimate the joint effects of treatment and smoking in a cohort of patients with HIV in the US. This is not such a timely question at the moment, but now we're pretty convinced that treatment works really well. And regardless of your smoking status, you should definitely do it. And smoking's bad for you, and you should definitely not do that. But at the time, there's this idea, the sense of degrees of badness. Is smoking especially bad for people who are either on or off treatment? And so the parameter of interest that we were looking at was a set of 3 hazard ratios. They compared the time to death that would have occurred under these 3 exposure plans. 1, initiate therapy and smoke. 2, initiate therapy and don't smoke. 3, don't initiate therapy and smoke. And so you could think about this. And then the reference group was, of course, the exposure plan, don't start treatment and don't smoke. And this is the parameter we might get in a 2x2 factorial trial of smoking and therapy. No one's going to randomize people to either of these exposures now, but I find the idea of this 2x2 factorial trial really useful to think about what these parameters actually are. And so to estimate these hazard ratios using observational data, which is what we had, we have to assume that we have this exchangeability between people experiencing each exposure plan at each time point. And we are going to relax that to be conditional on covariates. This is the standard no unmeasured confounding assumption. We also need to have exchangeability between people under observation and those lost. And not written on this slide, but sort of hopefully implied, is that we need exchangeability between those who are under observation and who never made it into our data set at all. And then finally, that our variables of interest are measured without error. And of course, this is where I'll focus today. This is the application of this new method. I should say the whole selling point here is that it's not a new method, an old method applied differently to a measurement error problem. The data I use for this are from the Centers for AIDS Research Network of Integrated Clinical Systems. It's a network of people being treated for HIV around the country in sites shown here. And importantly, I will abbreviate this CNICS because that's a really long phrase to say each time. So CNICS collects data on HIV clinical care regarding medications, labs, diagnoses, dates of death, patient-reported outcomes, and more, most of which comes from the medical record itself, except the patient-reported outcomes, which are collected separately. And to be included here, people had to enter between 98 and 2011, and they had to enter the study before starting treatment. And so we felt pretty good about the dates of death and treatment initiation. But smoking status was really hard to measure in this cohort. And in fact, what we were trying to use was the diagnosis codes provided in the medical record, where providers would kind of note in the medical record if someone was a smoker or not. And we knew this was a really terrible source of exposure data, but it was all we had to answer this question. Luckily for us, there was a subset of patients who self-reported their smoking status using a separate questionnaire as part of these patient-reported outcomes. And they did this as study entry and at various times of our follow-up. We're restricting our attention here to the measurement at study entry. And it's interesting because usually we think of self-reported exposures as the error-prone exposure value. But here, the provider-reported smoking was thought to be so terribly measured because if it was on the record, that was probably right. But what we thought was that a lot of providers wouldn't ask about smoking or wouldn't note it in the record if they did. And so we were probably missing a lot of potential smokers that way. And so the patient reported outcomes, because they weren't face-to-face, they were done using tablets, non-interviewer conducted. We thought that that might be a better proxy for the true smoking status. So now this is setting the stage for you. We had this provider reported smoking for over 12,000 patients. And then we had patient reported smoking, which is our gold standard for the subset of just under 3,700. And we'll treat that subset as an internal validation study. So bare minimum of notation here is that we have these two exposures, which I'm calling S and A. And here S is the smoking, and that's the exposure that is subject to the misclassification. And then we have our outcome variable T and some censoring. And so importantly, we have these three manifestations of exposure that I spoke about earlier. We have this true exposure, or our gold standard exposure, probably not true, which we're calling S, which is available for everybody with patient-reported outcomes, so the subset of 3,700. We have S prime, which is our error-prone exposure measured on everyone. And then we have S star, which is the exposure we use for the analysis. Now, for people in the validation sample, we're just going to set S star equals to S because we have their gold standard exposure. For everybody else, for now, we're going to let S star be missing. So now this looks like a missing data problem. Now let's look at the validation sample a little bit more closely. Of the 3,600-ish people in the validation sample, just under 1,600 smoked according to the providers, while 1,687 smoked according to self-report, which is much better than I was expecting before I looked at these data. So it gives us these sensitivity and specificity values here, which are not great, but perhaps not as horrible as we might have expected. And as we were discussing earlier, we get this confidence interval around those values. And those are fairly tight because we had a pretty big validation sample. So our aim here, as I mentioned earlier, is to estimate these joint effects of smoking and treatment using a marginal structural Cox model, which looks like this, where our effects of interest are the hazard ratios corresponding to EXP beta 1, beta 2, and beta 3, or beta 1, beta 2, and this joint effect here, which is the sum of all the betas. So that's what we're going for. But now, because S isn't available for everyone, we have to use some of the information in S prime if we want to avoid limiting the sample to people with patient-reported outcomes, which, by the way, we could do. We would just have a much less precise result. We don't want to throw away data on the rest of these 12,000 people and just limit our study to 3,000 or 3,600 when we have the rest of our outcomes and covariate data and treatment data on the full 1,200. And so one thing we could do we could estimate our inverse probability weighting approach, which is how we're going to fit the marginal structural model using S prime, the observed outcome rather than the true outcome. So that would use data from everybody, but it would use this potentially mismeasured version of the exposure. And then we could apply those weights to estimate the hazard ratios for the exposure between S prime and the outcome. Again, suboptimal because we know that exposure is subject to error. Now, what we'll do is we'll use our, I'm reminding you here of the difference between S, S prime, and S star. We'll use this idea that the validation sample is this setting where we have complete data on S star for people in the validation sample and missing data on S star for everyone else, setting this up like a missing data problem. And what we'll do is we'll use multiple imputation to impute S star based on the potentially mismeasured outcome S prime and other covariates for everyone who's not in the validation study. So we have a validation study where both outcomes are available. Everybody else gets S star imputed based on S prime and covariates. We'll do that M times. In this analysis, I think I did it 100 times. And we then perform the analysis in each of those imputed data sets and summarize results across them. This is a standard multiple imputation approach. Now that we've set up this problem like a missing data problem, you can use standard software to do this analysis. And there are simple implementations of multiple imputation in SAS and R. And I haven't used Stata, but I'm sure they have a simple implementation as well. And so first, I'll show you some example results if we assume no measurement error. So we essentially use S prime in the analysis. Up top, these are the crude results that don't account for confounding. Down at the bottom, these are the results that account for the confounding for both exposures. And the story here is that, let's just confine our attention to the bottom panel, is that it looks like smoking might be protective if you're not getting treatment, and there's really no effect of smoking if it's combined with therapy, and therapy here is treatment. And now let's look at how the results change after we account for the measurement error. Again, let's confine our attention to this bottom panel where we're accounting for the confounding as well. And now appropriately, smoking looks like it's bad for you if combined with no treatment, which is probably good. And I was kind of interested to see that when combined with treatment, smoking didn't really appear to be harmful. It might be that our window for this study was so short that there just weren't a lot of events. I think we looked out over 5 years here. It would be interesting to sort of interrogate this and see what's happening. But I was really interested that the direction of this effect completely changed for the people who were not getting treatment. And now, because we did this correction for the measurement error using a separate process from our outcome model, we could fit that. So instead of fitting a Cox model, we could instead make these risk curves. These are just the complement of the survival functions for each group. And these are both weighted to account for the confounding. So this is just an example to show that if you want to switch out the type of analysis you're doing with this approach, it's nice because by framing this using standard software as this missing data problem, you can apply that to whatever your final model might be. The last note that I want to make here is that coming back to our earlier discussion, accounting for measurement error, really accounting for any bias requires assumptions. Measurement error is tricky because we have to assume transportability of something between our validation study and our main study. Here, because we use multiple imputation, we assume that the predictive values between the validation subgroup and the main study were transportable. So that's given by, specifically, we assumed that S star was independent of inclusion in the validation study given your mismeasured exposure and Z. So in real terms, what that means is we assume that there wasn't like selection into this validation study conditional on your your true smoking status. So it's not like the people who were actually smokers and lied about it to their doctor were more likely to self-select into our study, or vice versa. So this implies that the S star is missing at random in the main study. If this is violated, then S star would be missing not at random, and our approach might have some residual bias. A design note here is if you're designing a validation study on the front end instead of creating one from existing data, it's important to note that you would have this assumption met by design if you randomly select the validation sample. And this is, a nice reminder that the random sampling of the validation sample ensures this type of exchangeability and expectation. Another way around this is if you don't have that option in the design stage, is that you could ensure that you had measured all joint predictors of inclusion in the validation sample and true smoking status. And if you include those in the imputation model, then this concern is alleviated. A final note when using something like multiple imputation and related here is that the imputation model has to be congenial or compatible with the analysis model. And in practical terms, what that means is, I didn't actually show you the imputation model, but the imputation model itself should include all of these variables Z that affect whether you're included in the validation study and the outcome, and the true exposure status, as well as any confounders that show up in the main analysis, as well as the main outcome, the outcome from the main analysis. And here, because this is a time to event outcome, we use some indicator of both the event times themselves and the cumulative hazard function at that event time. So all of this, we go into much more detail in the paper, but I just wanted to note there that when you're assuming this transportability of the predictive values, it's really important to think about these covariates Z that might affect who's in the validation study. There are other approaches that allow you, instead of transporting the predictive values, to transport sensitivity and specificity, which seems to me that it might be a more palatable assumption to some people, myself included, because it's easy to think that the measurement properties themselves might be more likely to be transportable than the predictive values. We had a paper out in AJE last year, I think, about flexible approaches to account for measurement error. And I don't think marginal structural models was in the title of that one, but we essentially used a very similar approach where we transported sensitivity and specificity rather than the predictive values, which I think is a bit more flexible. So finally, multiple imputation is one approach suggested here, but thinking about measurement bias and the potential outcomes framework lends itself to a host of other approaches. Really, any approach you could use for missing data, I think could usefully be considered in this framework to answer causal questions. And so with that, I'll take another breath and I will stop for a moment to let you all ask questions or attack my premises or whatever, whatever floats your boat.
Thank you so much, Jessie. That was very interesting indeed. And I see a question there from Jim Young. Jim, I'll let you speak up.
Hi, Jesse, it's Jim Young here. I'm kind of interested that you go from what is essentially a Bayesian approach, a full probability approach using multiple imputation, and then you switch over to something that is much more frequentist, relying on consistency arguments with marginal structural modeling. What would happen if you just carried on being a Bayesian? And I kind of have this idea, though I've never tried it, that you'd end up with everything embedded in a giant Markov chain using the G formula, and you wouldn't have to work with multiple data sets because that's what the Markov chain would be doing for you. Have you ever thought about that? Would it work?
I have not done it. I have certainly thought about it. I think if you wanted to be a full Bayesian
Oh, I do.
As you do, I don't think you would run into any barriers doing this there. I'm just trying
Why don't we do it sometime, Jesse?
What's that?
Why don't we do it sometime?
I think we should. I think
All
it
right.
would be fun. I think we would run into unexpected challenges, but that's part of the.
I'm sure, but I don't know what they are. That's why it would be fun.
I think similarly, you could not use multiple imputation here, right? You could use other like semi-parametric approaches to deal with missing data, and stay more on the frequentist side of things. But I'm notorious for accidentally blurring the lines between Bayesian and frequentist analyses, which I know is very against the rules if you're a true Bayesian.
I don't know. Stephen Cole does it all the time. I mean, you know, there's sort of, philosophical kind of issues here, and then there's just being practical. I don't see there's anything, wrong with your approach. It's just I want to go the whole hog Bayesian, largely because I just want to know if it works and how hard it is to do.
I think it is appealing because it would allow you to sort of account for many sources of bias. If you had priors on other things you wanted to include to account for other non-identified sources of bias, it would be convenient.
Yeah, and also I tend to work with really much smaller data sets relative to the complexity of the problem.
That makes sense.
Can I ask you another question, Jesse? Not as a statistician, more as a physician epidemiologist. I sort of, would the implication be that every test that we do, we often don't use the gold standard measure for any test? So does that mean that we should be using this approach to sort of account for the potential measurement error in any conventional measure? I mean, that could be for blood pressure, it could be for so many things.
Yeah, I mean, the should in that question is tripping me up. I think if you had asked, is there measurement error and potential bias due to measurement error in any analysis due to use of those measures? Probably, but then you have to ask yourself, from a practical standpoint, when will it matter?
Mm-hmm. Mm-hmm.
And that's something that, it could be, you could sketch out a sensitivity analysis and prove to yourself that in this case, the amount of error you expect is so small, you don't expect it to play a role.
Mm-hmm.
If validation data are available, and this has been an interest of mine in the past few years, of thinking about how to combine validation data from outside your study, say someone at McGill did a validation study and I want to use it at UNC, how appropriate methods to transport information from external validation data sets in.
Yeah.
Because once you can do that, then it really lowers the burden, the barrier to incorporate some of these approaches.
It's very interesting. Thank you.
Thank you. Claire, you have a question.
Yes, thank you so much for your presentation. My question is not going to be very fancy. I have the impression that the method you presented could help me. Actually, I've been approached by a research team. They told me, oh, you could do some kind of propensity scores. We want to assess our intervention with observational data. I said, oh, sure, that's super easy. You'll see. And then I discovered that actually on their administrative database, they have data on building of the intervention. So they have data on whether persons are in the exposed or in the unexposed group. But we did first a validation study, and we actually saw that people don't bill. Like it's the administrative data from France, and actually I don't know why, but less than 50% of doctors do bill within the 3 months period that they were required to, and 20% actually never bill. So I started telling them, like, how are we going to do the target trial framework? We don't know when is the intervention. So are we going to try to find that there is an exposed and an unexposed group? But actually, I don't know when it happened. I'm not sure who has really been exposed. So at some point I told them, we will just publish a methodological article for policymakers telling them, hey, stop doing these crazy interventions, not thinking how we're going to assess them. Then I thought, perhaps we should think about computing some kind of e-value that would be, instead of the power of unmeasured confounder, we will say what would be the most misclassification we should have to revert our results. But after representation, actually, I'm thinking, oh, because I could use as a validation study the study I told you, which was on another set of intervention that could be thinking, okay, French physician bill as bad as that. And for the intervention I'm interested in, I guess I need to read your paper and see, because I think, so my problem is that the exposure is almost unmeasured now. Like I will have very few people for whom I know. So if I think 50% of people, if I think that my validation study, that I have a validation study that I can extrapolate the way their behaviors for another study to the study I'm interested in, would be that so 50% of people will be built within 3 months. And I was thinking I could say, okay, we don't know when the intervention happens, so we can just say during the amount of time of we cannot do a pre-post because we don't know when it's pre, when it's post, but we could say intervention group had more or less readmission, for example. That was already like, but anyway, I have the impression that you're opening some ways to go around it with the methods you're presenting, even though I'm still perhaps at just the beginning of the problems.
You know, I mean, I will say that I think your problem is, it sounds complicated for several reasons. One of which is that you have times that are mismeasured. So that's something I've struggled with as well. When you have, you don't only know, it's not only that you don't know if they're exposed or not, but you don't know when. Right. And so I've sort of played around, if you have a validation study where you do know when, could you impute the time? It's hard, but I think it probably could be done thoughtfully. Okay. But that's something I have empathy for you and trying to deal with that problem. I think that it's a good one. It's a good puzzle.
Okay, thank you so much.
You're muted, Nandini.
I'm sorry. I just want to say thank you. And I just wanted to follow up a bit on what Jim Young asked. There's a sort of Bayesian inspiration in these methods, but then you're finally using a frequentist approach. I'm wondering what software you use to carry out all these analyses.
Yeah, that's a good question. So this is sort of a story of my recent career trajectory. Is I started out using SAS for everything. I've switched over to R. So now I've done this specific analysis in both. I haven't used Stata or tried to implement this specific analysis in Python, but I imagine that my motivation was that any software package that has like a multiple imputation package or program sort of built in should be able to handle this once you set up your data in the right format.
So within R, you're using like a combination of whatever mice and
I use mice, yeah.
And whatever GLM or Cox proportional has its model.
Yep, I used mice to do the imputation and then logistic regression to build the weights and then a Cox model to do the final marginal structural model as a Cox model.
Okay. All right. Yeah. All right. So all programs that we have access to, so then therefore your methods should be widely accessible as a result.
The goal of this project was really to use methods that were available and also familiar.
I'm not seeing any other questions from the audience. Okay. I just indeed want to ask you something that something else that was on my mind. So, like I was saying, there are some ideas I feel that we keep repeating, like, and I feel the biases that come up are selection bias, measurement error that you've talked about, and then modeling of heterogeneity. So introduction of random effects, which are essentially missing data to measure heterogeneity. And so all of these are somehow missing data problems. And you've talked about measurement error today. Have you indeed dealt with the other two problems? Kaberi herself mentioned one, which is the gold standard missing problem.
Yeah, I mean, so if the question is, have I thought about other biases due to,
I mean, have you used the method, the concept that you approach to correct for selection bias? Or
I mean, the short answer is no, I haven't used multiple imputation to account for selection bias, although, so there are two things. So I've tended to approach it as a missing data problem, but use inverse probability weights because I'm often doing weighted analyses anyway. And it's easy to combine like inverse probability of censoring weights with inverse probability of treatment weights. That said, I worked on a paper a few years ago with Daniel Westrake about multiple imputation of potential outcomes, where he sort of does this imputation of the potential outcomes explicitly. And so that, I think we were thinking about confounding, and I'm not sure if selection bias made it into that paper, but it may have. And I think all of the concepts about, you know, imputing the potential outcomes, thinking about confounding would go through to selection bias.
okay. Right. Kaveri, do you have another question? All right.
It was a great talk, and we made it up to 27 people, but I think even more should have attended. So thank you so much for organizing and just for.
Thank you very much.
Yeah, thank you for the invitation. This was fun.